All right, let's get started. Welcome to the June 2021 OpenZFS leadership meeting. It looks like we don't have too many attendees and don't have too many items on the agenda. So well, I won't say because I don't want to jinx it. But let's get started. And we should have time if folks have other things that they want to discuss or questions that are not on the agenda. First was a question from Rich. I don't know if you're on, Rich, but they were asking about ZTour. Is anyone working on it or an equivalent? I think you remember that from many years ago, Developer Summit Conference. There was a demo of ZTour, which was like a facility for examining the on-disk format using something like a debugger, like using MDB maybe.
I think it was using Fuse or something to actually let you browse it as a
Oh,
file
that's
system.
right.
Isn't that the one that Don Brady did?
Yes.
Yeah, I think you're right. And I don't see Don on here. As far as I know, Don hasn't done any more work on it. Does anyone know of other similar projects in that space of like ZDB-like things for examining the on-disk format? All right, well, it's definitely an interesting idea, and one that we're thinking about a little bit in the context of the ZFS object storage stuff. So I'll maybe come back to that when I give a little update on that. But I guess maybe I'll give you a preview. So there's additional on-disk state, or maybe it's not disk, but in the object storage state that is kind of below the existing ZFS on-disk data structure. So we need to come up with some way to examine it, either using ZDB or using some other facility. So if folks have ideas about like how you would like to see that or do that, then maybe one place to explore that would be with this object store metadata, since there's a lot less of it than ZFS. So if you want to do something new, we could start experimenting with how to do it with object store metadata. Hooking up to Fuse seems like maybe a lot of work, but I don't know. Don, I guess we'll ask Don.
Yeah, because they did it at the more recent Dev Summit. They revived it, and the team worked on it, and they won the Lego spaceship or whatever. And they had something that they could actually demo, and it looked cool. So.
Yeah, I don't recall who else worked on it with him, but that if you're curious about it, that would probably be a good resource to go check who worked on it during that hackathon.
I think that would have been 2018.
Sounds right.
Sounds right.
Maybe a few clicks will bring us to it. Let me see. Hackathon. I don't see in 2019. I don't see it in 2018. Let's see, 2017. All right, it was 2017. ZTour mixes ZDB with Fuse. Participants were all from Delphix. Don, Brady, Pavel, Zakharov, and Prashant Srinivasa. Yeah.
So I guess it's been a while.
Yeah, it's been a while. If folks are interested in this, I will try to see if Don will come to the meeting next month. He's going to be working on ZFS more as part of the object storage project that we're doing. So I think he and a few other folks would probably find it useful to attend this meeting for other reasons anyways. Cool. All right, if there's nothing else on that, we'll move on to the next item, which is the Linux user namespace support. Alan, is that your item?
Yeah. So we've posted the first PR for this, and it works. I'm gonna have to look at the test failures because it was passing all the tests when I tested it. But basically, if you enter another user namespace, this changes the ZFS and Linux code to, instead of, there's a check used in a bunch of places in ZFS in global zone, and on Linux it was just defined to 1, so you were, no matter what, you always were in the global zone. We changed that now to actually look at which user namespace you're in, and if it isn't the root one, to return that you're not in the global zone. And so with that, if you run, unshared -U, and you're now in a different user namespace, when you run ZFS list, you can't see any data sets. But you can delegate data sets to a namespace. So if you set the zone property to on, and then do ZFS user NS add and the namespace ID to the dataset, then when you run ZFS list inside that dataset, you'll be able to see only those, similar to how zones and jails work on Solaris and BSD. And it works so that you can mount the datasets within the namespace if you have a mount namespace as well, so that it can work with something like LXC containers, so that inside the container you can, as the root that's not really root, can do whatever you need to do to the data sets, and all the same rules apply as with jails and zones. You can change most of the properties, but you can't change the quota and the limit on file systems and snapshots and a couple of things like that. So basically just maps the existing zones and jails code to what the equivalent is in a Linux namespace.
That's cool.
Yeah,
So
and that was
like
sponsored by Buddy, one of the CI company, and they want to run people's CI in containers, but they want to use ZFS.
Cool. Are you looking for code reviewers now?
Yes, it's ready for code reviewers, but also interested in people with similar use cases who might. I guess one question is, does suddenly ZFS list not showing stuff when you're in different user namespaces break anything for anyone? I don't think so. Once you're in a different namespace, you kind of expect not to have access to the stuff from the original global namespace, but it will be a change in behavior. And if it's problematic, we might have to protect it behind a module parameter or something. But yeah, if people want to test it out and see how it works or whatever, interested in feedback.
Cool. And this is in the area of like platform specific kernel code. So I've assigned Tony Wynn to be the maintainer for this. So you can work with him if you need help finding reviewers or getting reviews.
Okay.
Cool. Questions about that? I think this will be a great feature to see, to bring Linux kind of up to the same richness of functionality that we have on the other platforms.
Yeah, I think that's really neat. Alan, just to clarify, it sounds like from what you said, it sounded like we need to enable this, right? There's something that we have to set to enable this feature, or is it going to be the default?
Not currently. Currently, it is the default, but if it breaks things for people, that might. Okay. I don't think anybody assumes that they can access stuff as ZFS when they're in, once you're in a different user namespace, you're not root anymore. So unless you've done ZFS allow or something, you wouldn't expect to be able to do much in the way of ZFS commands anyway.
Got it.
So yeah, this is on by default, but if that change in behavior causes problems for people, we might have to protect it, but I don't expect so, because as soon as you enter that namespace, you're not really root anymore, and so you don't expect ZFS to work anyway.
Got it.
Alan, in terms of the testing, is there any change required on the tooling side? I have in mind you trying this with Podman, and it underneath it uses the graph driver. Does it need any change to the driver to actually use it?
Not really. Like when using it with LXC, you have to allow ZFS, like whitelist ZFS in the list of file systems that are allowed to be used inside the container, which is just an AppArmor config file on Ubuntu. But outside of that, no, there's when you're inside, ZFS just works the same. It's just you're limited to the data sets you're allowed to see, which are the ones that are delegated to you and have the zone property.
Okay, so the property needs to be set.
For you to be able to mount it and manage it, to mount it inside the namespace, yes, the zone property has to be turned on, similar to what you would do for
Okay,
Solaris
so
or BSD.
that would require change in the graph driver inside the Podman to actually mark the data set that is inside the container.
Right. If you want the users inside the container to be able to manage it, like if you just mount it from the host to the directory that it's chrooted in or whatever, then that would still work. It just, you know, it depends if you want user inside the container to know that they're using ZFS or not, or be able to see the data sets or not.
Okay, okay.
Like I know with jails on BSD, half the time I just create the data set on the host and mount it to the right spot relative to the jail's root. And the jail doesn't know that it's a separate data set other than, you know, the file system ID is separate or whatever. But it doesn't know the name of the data set or anything. It just shows up as, I think, restricted or something like that in DU. Or you can actually delegate it so that root in the jail can, you know, ZFS set compress equals or whatever.
Alan, you mentioned like the mount namespace and having like that capability of being able to mount the data set. So you have to be in the mount namespace and you have to use a user namespace, or if you don't set up a user namespace, can you just do the mount namespace and allow a delegated data set to be mounted?
If you're just in a mount namespace, then you would still be root from the original namespace, so you can just do whatever you want to do, right?
So it doesn't restrict you in that case.
Yeah, so in global zone is specifically the user namespace.
Okay. Yeah, the Linux namespace stuff is like, there's so many combinations. It doesn't map well to like zones or jails. So it's always interesting when you start to kind of like look at the kind of permutations there.
Yeah, so we did the user namespace because that's really when you're deciding, is this the real root or a made up root user? Right, like are you real root, or are you some user who ran unshare or whatever and are running an unprivileged container that is just pretending to be root?
Cool.
But in general, the only thing that was really required was setting an extra flag in the VFS bits to say this file system is aware of the namespace stuff, so that it handles the user ID mapping or whatever. So that, you know, when you're inside the namespace, you're actually running with the virtual users inside that namespace have very high UIDs, but that are mapped to regular ones inside the namespace. So ZFS has to know that, you know, UID 256,001 is actually inside shows up as, you know, user ID 1001 or whatever. So that when you ls the files you create inside, they have the name relative to the namespace, but you know, on disk, those are owned by the user ID that's the real one. If that makes sense. And we've added a bunch of test cases, but if people have suggestions for other test cases, we'd like to make sure that we cover all that.
Were there any existing test cases for like jails or zones that you could port over?
There was one, I think 1 or 2 existing Linux tests for something to do with namespaces that we extended. And then that for jails, I don't know that there are any test cases for jails, and we might want to look at adding some.
There's a bunch of places in the suite where blocks of code are conditionally marked out like is global zone, which originally was to run with zones. Have you been able to try to activate any of those code paths?
I wasn't aware of them, so didn't know to try.
Okay.
But
Are you
we
talking
can
about
take a look
within
at
the
that.
test suite, John, or
Yeah.
in the kernel
yeah.
code?
No, in the test suite.
Yeah, I think that what you're talking about, John, is like you could run the test suite from within a local zone, and it should more or less work with the, but like some tests don't run.
Right. Or have to handle devices differently.
Yeah. Yeah, so that would be interesting to see, like, because I think that covers, the vast majority of the tests do, or at one point would actually run within a local zone on Solaris.
Right.
So you might look at doing that on Linux.
I mean, bear in mind, it's been untouched for like a decade.
Yeah, so it might not totally work, but that might, I don't know. If you think that actually gets us useful test coverage, then that would be a reasonable approach to take.
Yeah, I see there's some like ZFS Destroy that checks is global zone.
Exactly.
And those might be useful to hook up just to make sure we prove that, you're allowed to destroy the data sets that are delegated to you and you can't destroy data sets that aren't. We tested that by hand, but getting those tests hooked up would be good. I'll have to look at those.
Cool. Other questions about delegation or containerization in Linux? All right. Why don't we I can give an update on where we're at with the ZFS object storage stuff. But if folks have other questions or topics, why don't we bring them up now, since I might get into a sprawling monologue and chew up the rest of your time at the end. Any other questions or topics?
So with ZREPL, we have repeated reports of ZFS dry sends reporting a very large UN64 as size estimate, and it seems like it's a negative. Is it called underflow or overflow? If we go negative, I think it's still called overflow technically. But yeah, there appears to be some bugs with that, and we currently have a user who is like setting the data set aside so we can reproduce the case. We just need to hook him up with someone who can tell them what to do.
So this is like ZFS Send -NV, and
yeah,
then
exactly.
the size is 18 or 16 EB or whatever.
Yeah, exactly. So
yeah, why don't I would say file a issue if there isn't one already, and then ping Paul Dagnelli. He should be on Slack. The first step is to figure out, like, there's so many different code paths, like modes of send and send estimation. So if you can include like the exact command that's being run, then that'll help. Like, presumably it's not it's not what's it called? It's not redacted send probably, but like full versus incremental and all that, and like from bookmark versus from snapshot. There's like different code paths for all of those.
Okay, yeah, I'm not sure how long they can hold it aside. So, but I assume like a Z stream dump or something that wouldn't help, right? Because then we already have the
Yeah, probably not.
Yeah.
Um,
Okay.
but at least that basic info will then tell us like what additional metadata we would need to see to figure out why it's going wrong. And then probably we could get that from ZDB, and then they could, you know, destroy their stuff.
Okay. Yeah, I'll create an issue.
Cool. Other questions or topics? All right, then I'll talk a little bit about the object store stuff, which I think I mentioned 2 months ago. We're now well on our way to initial implementation. We have most of the team here at Delphix is working on this project in one way or another. So Mark and Seraphim, who are on the call, just joined us this week, and they're going to be working on the new cache component, the ZetaCache, with me and Tony Wynn and John Kennedy are working on the performance aspects, so performance evaluation, which I both look forward to and dread seeing the results of that because we're still very early in the implementation, so there's lots of stuff that doesn't work as we know it needs to get good performance. So we're folks might not remember from 2 months ago, so let me give you a brief overview of like what we're doing. Basically, we want ZFS to be able to consume object storage rather than block storage, or like as an alternative to block storage. So you know, typical use case might be you're using ZFS in the cloud, like say in AWS, and you want to use S3 as the backing storage for, you know, probably primarily for cost reasons. Although kind of after this initial project, we have some more awesome and crazy ideas that will take further advantage of the shared nature of object store, which I'll talk about later. So the key and tricky thing about our use case is that we want to be able to do this with databases, which are you know, doing small random writes with small record size and compression, and everything is small and tiny. So we can't get away with just saying like if you're doing that, you're using it for backup, and you're gonna just set, you know, record size is at least 1 meg, and we'll have one object per ZFS block. That would be like relatively straightforward. But we want to be able to use continue using small record size for the databases that we're storing, which means that we need to combine a whole bunch of blocks, like a whole bunch of like 3 kilobyte blocks into one, you know, 1 megabyte plus size object for the object store, which means that we need to worry about like, how do we free these? So, you know, we got to keep track of like, here's all the blocks that need to be freed but haven't been freed yet, and then kind of consolidate that so that we can we need to batch process that, so that for every object that we have to read and then rewrite to remove the freed blocks, hopefully we're able to free a whole bunch of blocks within the object, not just 1 or 2. So that's kind of one half of what we're doing, and then the other half is for a lot of use cases, we still want to get good performance. So the object stores, you know, generally have really high latency for get and put requests, like dozens of milliseconds at least. And in a lot of cases, if the data, so for writing, we can kind of ignore the latencies because we're batching everything up into transaction groups, right? And we just have to worry about, well, what about synchronous operations? Well, we can use the existing ZIL and have like a local disk that gives us good performance for the ZIL still. But for reads, you know, waiting dozens of milliseconds for all of the reads that are not in the arc would be really, really slow. So we're going to use something like the L2 arc, caching blocks on local disks. But the L2 arc, it can't get very big in terms of number of blocks that it can store because it uses so much memory per block. The L2 arc works pretty well if you have large record sizes. But again, like having small record sizes causes lots of performance challenges for us. So in particular, you might want to be able to have a cache that's like dozens of terabytes at least, which means that even if we were to like kind of super turbocharge the way the L2 arc stores its metadata, you still wouldn't be able to keep that entirely in memory. So we have to deal with an index of the cache that doesn't fit entirely in memory. So that's kind of the big challenge of the caching subsystem. So the way that we're implementing this, all this stuff, the cache and the talking to the object store part, is going to be, or it is, through a agent process in userland. So like the kernel is making read and write requests that are calling up to the agent, which is then, you know, checking in the cache, going out to the object store over the network, doing the background processing of like background freeze, managing the on-disk index of the cache and all that stuff. And the agent is all written in Rust. So let's see, what else should I tell you guys? We're pretty far along with getting things to kind of basic functionality. We just started on the cache last week, and we have something that kind of sort of almost works for like a little while. And I might be able to show you a little demo if people are interested, but why don't I pause and, the other thing that we did is we opened a issue that has an outline of like the project, that kind of stuff that I just mentioned, and then the user interface for how you would create an object store based pool. It's a little different because you need to be able to specify like what's the object storage endpoint, you know, like what's the name of the other machine I'm going to be talking to, and what are the credentials that we're using to talk to it.
Hey, Matt.
And we're doing that with ZFS properties.
Did we update that for the new role property?
I don't think that's updated yet, but we should ask.
Okay.
Ask Manoj to do that. Yeah. Or Paul. Yeah. Yeah. So we have some enhancements in progress that will let it like figure out the credentials based on the role that's assigned to the instance in AWS. That'll make it a little easier. Christian, I see you have your hand up. Questions?
Yeah. So I've thought about ZFS and object storage 1.5 years ago, and I think one concern was cost analysis and cost prediction. So because you pay for the individual requests as well, is that at all a concern in your design, or like how do you model costs and take that into account?
Yeah, I mean so we're primarily thinking of it for our use case by comparison. We're comparing it to using EBS, you know, the block storage in Amazon, and the per byte cost is much lower. It's like about a quarter or a fifth or something like that, compared to the cheapest EBS storage. But yeah, there are per operation costs of like get and put. We looked at that kind of from a theoretical point of view. The good thing is that the costs, as long as you're using it like within AWS, like you're using S3 from a EC2 instance, they don't charge you for the throughput. They just charge you like a per request fee. So those are usually not too high compared to everything else. As long as your as long as your objects are big, right? Because it's like, well, yeah, I'm writing at full network bandwidth of 25 gigabits per second, but it's with 1 meg or 8 meg objects, so the actual number of requests per second is like pretty manageable. I mean, it's not nothing, it adds up to like a few dollars a month or whatever, but you're paying $25 per terabyte per month for the storage, and you're paying a lot more than that probably for the instance to run it at 25 gigabits per second. So it's not too bad. We did I don't know if Paul, I think Paul's not on here, but Paul is working on a facility like MMP, the multi-mount or multi-modifier protection for the object store. And that's going to be like mandatory. Like, right now the MMP is like off by default. You have to like jump through some hoops to use it or whatever. But for object store, it's just like so dangerous because like everybody has access to it, very easily, that it's going to be always used. And we did have some interesting designs around that, because if you're heavily using the pool, then hey, like paying a few bucks a month doesn't really that doesn't matter. But if you're not using the pool, then having MMP be putting down its heartbeat even just like once a second, it does add up to like non-zero dollars per pool. I mean, if you just have one pool, then it's no big deal, right? It's like $3 a month or something like that. But all right, so now let me get to, if you don't mind me rambling on a little bit, the end goal for this is not just you have one pool that's on object store. The end goal is that you have essentially like distributed ZFS, where you have like a big system of interconnected pools on different machines, and they're all consuming storage from the same object store. And the real key thing that we want to be able to do is to have like a snapshot that's in one storage pool and create a clone of it in a different storage pool. And the clone like references blocks that are in the parent storage pool without having to copy those blocks, using send and receive into the child pool. So you might, in this new like object store based world, creating pools becomes almost as cheap and easy as creating file systems is today. And you can move the pools between, between VMs. So it makes the overall system much more flexible. And in that world, you might end up with lots of storage pools. And so you might have lots of storage pools which are idle most of the time. And so the cost of like writing out once a second an object for each pool might actually become, noticeable to our customers' wallets. So Paul has done some work to design that so that the basically instead of having to write out a heartbeat for each pool, we only have to write out a heartbeat for each bucket that this agent is connected to. So the agent manages like all of the pools are managed by one agent process on the machine. And so that way, like, basically each pool will have an object associated with the pool that says, you know, I am owned or was most recently owned by this agent. And then the agent will have like a object in the object store that says like, I'm still alive every second. So that way, you know, you only have to have a heartbeat, basically like, you know, one heartbeat per VM that's part of the system rather than one per storage pool. So that is a point where that did come into play.
Yeah, if I can add something else too, Matt.
Yeah.
And the other thing, going back to cost, I mean, like this is kind of why the Zetacache is such a big component of being able to like cache the majority of the blocks that you might be using for that specific file system, so that we don't have to go back to object store. We get the big blocks going to S3. You're doing a few operations there, yeah, and then and the majority of your work is kind of happening locally through some EBS volumes. The other thing that to note about the Zetacache and part of the design is, unlike L2ARC, which is kind of dedicated to your pool, this is a global type of cache for all the pools being managed by that agent. So as,
or at least all the
Matt
pools
was
that
talking,
want to participate. Yeah.
Yeah, exactly. Yeah. So the when we get into this multi-pool architecture, this Zetacache is kind of like a global entity that these pools will be able to register and say, I want to cache some blocks, and we're going to use, this whatever disks are, kind of backing the Zetacache.
Yeah. So for reads, I mean, for reads, you really don't want to be in the case where like I'm doing one read and that's causing me to get an object and then I'm not getting anything else from the object, because then you have huge, read throughput inflation, because it's like, oh, I'm reading this 4K block and it's causing me to go read this 1 megabyte object and I threw away, 99.9% of the data. You want to either be in the mode of like, oh, like we're scanning, like we're just bulk reading this whole thing. So yeah, like I read this one block and it caused me to bring in the whole object, but now the next 300 reads are also going to be to that same object. So we actually used it, and so it's fine. Or you want to be in the mode where I may be doing random reads, but they're all cached in the cache. So basically you want to have like either you have like 90% plus cache hit rate in this L2ARC like disk-based cache, or you're like doing bulk reads, or you're not using small record sizes. Like there's certainly lots of other use cases for this that don't have all these hard problems. And like you're storing video files, they're all in record size 16 meg, and it's just one record per object, and then like everything is much, much easier than the problem that we have chosen to tackle.
Are you envisioning to use this with the special VDEV or something for all the indirect blocks, so that you don't have the problem of having to read a 1 megabyte block to get the indirect block to tell you which 1 megabyte object you need to go fetch next?
So for at least for our use cases, we would always have some sort of block-based cache. So and making sure that that's at least 1% of the whole pool size is like pretty easy. So we would probably always have all the metadata, like all the indirect blocks, in the cache.
Yeah, that'd be the expectation.
Yeah.
Right, but you didn't envision specifically using the allocation classes to keep them separate?
No.
Okay.
Yeah, I mean the cache, it's like within the cache, there's definitely a lot of cool stuff that we can do to make it so that like it can handle things at different block sizes. Maybe I'll get into that in a couple of minutes, but in terms of like what's in the object store, we weren't doing any like we're kind of letting ZFS's allocation ordering kind of handle a lot of that for us, because I think that the way that it works, we can double check this though, is like, it's basically like it's writing blocks of one layer together. So like the ordering, I think, will happen to be like, first you get first we try to write all the data blocks, then we try to write all the indirect blocks, then we try to write all the L2 indirect blocks. So they'll naturally kind of be clustered together in objects anyways.
Right, yes, good point.
And the big thing about the special devices has two big benefits. One is like, you can have a faster device, which like, we don't have faster and slower like object storage. We have the cache to solve that problem. And then the other benefit of the special devices is you aren't trying to combine lots of big blocks and lots of small blocks together into one like metaslab allocator scheme. And so like, that's kind of a self-imposed problem, rather than a fundamental problem. Like that's the problem of how ZFS chooses to do block allocation. And we've kind of been making some dents in that over time, like with the ZIL embedded slog metaslab, basically like automatically carving out one metaslab to use for log allocations if you don't have a dedicated log device. You could imagine doing something similar to that, like, like I noticed that 90% of the blocks here are small, but you have some big ones. Let's carve out one metaslab for blocks that are like larger than 32K. But we can, with object storage, like the allocation part of it doesn't matter, right? Like you can put together big and small blocks into one object, and that doesn't hurt the allocator at all, because it's just like sequentially slotting them down into objects. We don't have to go like try to refill existing objects. Within the cache, now that's where it gets really interesting. So within the cache, the on-disk cache, the L2ARC, the way L2ARC works, it just like starts at the beginning of the disk, writes through the whole disk, and then when it gets to the end, it comes back to the beginning and overwrites what it was there before. So the allocation is really easy, and you can mix together large and small blocks, and everything is fine. But the eviction policy is horrible, and that has an impact on cache hit rate. And maybe that's okay for a lot of the time with the L2ARC, especially since like the kind of philosophy of the L2ARC is like, it's like an extension of the ARC, and you're going to get some hits and some misses, and it's like better than nothing. Versus for our use case, it's like, well, in a lot of use cases, you want to be getting like 90% plus hit rate in the cache. And if you go from 90% to 80%, that's like doubling the number of times that we have to go to the object store, which could have a really material impact on your overall performance. So we wanted to have a cache where we control the eviction policy and it's reasonable. So we chose LRU, which, it's not like amazing. It's not scan resistant the way the adaptive replacement cache is, but it's at least reasonable and easy to reason about. And so that means that we need to be able to choose what we evict, not just like have whatever get overwritten. Which means that within the cache, we're going to be left with, like as you're ingesting stuff, you're evicting old stuff, and you're leaving lots of little holes where you're evicting stuff and then trying to fill those little holes with the new stuff, which is basically the same as the problem that we have with ZFS on block storage and the metaslab allocator. And like, when you have tons and tons of small blocks, especially with compression, it gets really hard, and you have to maintain some free space, and you have to keep all your metaslabs loaded, and it takes up a lot of memory. These are all problems that are kind of specific to having lots of small blocks. Typical ZFS users where you just have like the default record size 128K, you don't really run into this. But if you're storing databases with record size 8K and you're using compression, and maybe you're using A shift 9 512-byte sectors, then these problems are very acute. So with the new cache that we're designing, we're going to be investigating and hopefully implementing some newer, better ways of doing allocation, which may be able to be transferred over to the ZFS proper, block-based ZFS. So what we want to do is divide the space up into slabs. And each slab would have allocations of all the same size. So like, let's say each 16 meg slab has things that are all, maybe they're all 1K or all 1.5K or all 3K or all 3.5K. And so then when we're doing allocations, we would find, like, we know I'm trying to allocate 3.5 kilobytes. So I'm going to go to one of the 3.5 kilobyte slabs and just get one from there. This should sound pretty familiar in terms of the memory slab allocator. That's exactly the way that works. And the meta slab allocator is kind of named after that. And there were some ideas initially about how we might do that, but those never really came to be. So we're kind of trying to get back to that place, at least for these small blocks. I think it'll be very helpful in terms of memory usage and like memory usage of the allocation state should be much more efficient. Like in the worst case, you have 1 bit per block to keep track of this in memory. And you can do better in some cases as well. Yeah, okay. Maybe I should pause my monologue here and see if folks have more questions.
I have another question.
Yes.
So I'm not totally clear how much like layering, like cross-layer hints you're doing there. Like how many hints are you giving from ZFS into the user space daemon and back? That's still like, I didn't get it from the explanation.
We right now there's not a lot of hinting, and there's also probably a lot of performance that we're leaving on the table in terms of the current implementation. What did you have in mind in terms of what might be necessary there?
I'm basically not clear, for example, how much of the metaslab allocator still is in place versus how much you delegate to user space and so on. None.
Yeah.
Okay.
So the metaslab allocator doesn't really have any place with like what goes into the objects, because we're just writes fill up objects, and then we don't go back and modify old objects except for to free stuff out of them. So we aren't like reusing them. So you don't really need a metaslab allocator for the cache. You could imagine using the metaslab allocator to allocate the space in there, but we decided to instead kind of do a from scratch implementation. So the agent that's managing the cache, it's not using libzpool. It's all from scratch. So it's just like all new code that's consuming the disk and doing writes to the disk from all new data structures that we're coming up with.
From the perspective of ZFS, like there is a new VDEV type object storage, and it has no allocation.
Exactly.
Okay.
Yeah. So from the kernel's point of view, it's like there's some new VDEV type that's a VDEV object store, and we have like special hooks in there to say like, oh, like if you're going to object store, then you don't need to do any allocation or whatever. Or I mean, the only allocation that you do is you allocate the block ID, which is just like I++, right? The block IDs just move forward and we never reuse them. And so that's very easy. And then when you do the write down to the object store VDEV, it's just like I'm writing to block ID, the next highest block ID that's never been used before. And then it just sends that request up to the agent. And then the agent is like packing together all these sequential block IDs into one object.
Okay, but the information, for example, about the object type or something is totally lost on the way.
Yeah. So all
Okay.
the agent's just getting like write this sequence of bytes. So it's just like, here's the size, please, here's the block ID, which is, you know, like the next block ID, please write it. So we like if we want the agent to take different action for different types of things like metadata versus data, you know, like indirect blocks versus user data or whatever, we could easily add that hinting into it, but we haven't got that sophisticated yet, and so far we haven't needed to. But if you have thoughts on like what we should be doing, that would definitely be, I'd love to hear them.
I think there's lots of academic literature on like predicting data block placement and so on. And if we already have the information about the object type, for example, like we don't have to do all the fancy prediction stuff, but we already know it's metadata or it's data and so on. So yeah, I think we can maybe could profit from that, but then again, it depends on your use case mostly.
Yeah, it depends on like how much profit there's to be had, right? Like after you've predicted whether it's metadata or data, what are you doing with it, and how much does that help you?
Yeah, for example, like you could have separate objects for data and metadata, because the metadata is supposedly changing much more frequently, and then maybe have another look at, okay, is this an allocation for an object set that is like 1 megabyte block size, or just an allocation for an object set that is 8 kilobyte block size, for example. And then maybe based on that, guess whether it's archival storage versus hot storage, and yeah, maybe tier that into different objects a little, so that you have better, I don't know how you call the metric, about like object utilization or something. You'd have to come up with a name for that. Yeah.
Yeah, so in terms of the object store, the biggest problem that we have is going back and freeing stuff. And the what you really want is for your frees to be very clumpy. Like you want them to be clustered into objects. So like, you know, we have 1 million frees, and you know, you have 1,000 objects, but those 1 million frees are concentrated in just these 100 objects. So we only need to read those 100 objects and then rewrite them to process the frees, rather than having them be, if they're evenly distributed over all of our objects, then it's like, well, I have to read and then rewrite every object, you know, the entire, you know, petabyte of your storage, which, you know, would really suck. I mean, you just can't do that very often. So, you know, you're gonna end up with a lot of outstanding frees, which, you know, the good thing is, unlike block-based storage, you don't have a finite size. So it's not like, oh, like you're out of space, now your pool is, now like you can't do anything because your pool is full and we got to go process the background frees. Instead, it's just cost, right? It's just that, you know, you're paying to store these blocks that are no longer going to be used. And so, you know, to be nice to our customers' wallets, you know, and eventually our wallets, if we, you know, hopefully end up running this as a service, we need to free it reasonably soon. So if we could predict, like what we really want to predict is, when will this block be freed, and which other blocks will be freed around the same time? If we could predict that, then, you know, we would say, like, for a given TXG, we can kind of choose how we map its blocks into objects. So if we were like, for this TXG, like, these are the blocks that are going to be long-lived, and these are the blocks that are going to be short-lived, we could pack all the short-lived blocks together so that when we go to free it, we only have to hit those blocks, we only have to modify those objects and not the objects that contain long-lived blocks. Hopefully, like the indirect block versus data block clustering that hopefully is already automatically kind of happening to happen will help us there, but I don't really know if that's the case. There definitely we could use some more research there.
Yeah, like conceptually it sounds right, but then if you do the try to group all the 3.5K allocations over here and all the 2K allocations over there, do you end up splitting up those?
Well, for that, so that's a different problem, right? That's for allocating all the 3.5K things here, you're talking about the cache, right? So in the cache, with the cache, we could have chosen to cache objects or to cache in big chunks, but for the cache, we chose to do everything block-based. So you can allocate and free individual blocks without incurring, additional work, just like you do with regular block-based ZFS. And so that's why you have the problem of the allocator being having all the same problems as the MetaSlab allocator. Yeah, so I mean, we definitely thought about all these things. Like maybe the cache should be allocating 1 meg chunks from the disk and packing a bunch of blocks into there. Then your writes will go really fast. But then, when you're evicting, it's like, well, if I want to evict part of the, some, but not all of the blocks in that chunk, then you end up in this rewrite.
Right.
You end up paying a lot of bandwidth to go read and then rewrite those chunks of the cache.
Then you're solving the SMR problem instead.
Exactly. And it's like, well, look, we already have something like the object store thing basically solves the SMR problem. So you want SMR, basically just use the object store type, use it as an object store, right? And I could imagine obviously we could be more sophisticated about it, but I would bet that if you took a SMR, a drive managed SMR drive, and just put XFS on top of it, and then had a layer that mapped from objects to each object is one file on XFS, and put ZFS object store on top of that, it would work great. Because at the end of the day, you're writing in these big chunks and then freeing the big chunk and then overwriting it. So the SMR level remapping is not going to have to do, it's not going to have to do a lot of work. But the advantage is you get you can be doing random writes, you can be storing a database on it, you can do whatever you want, and then the ZFS object store layer takes care of making sure that everything is actually happening in big chunks to the drive. It looks like we're out of time. Thank you all for coming to the Matt Aaron's ZFS object storage monologue. I hope you enjoyed my comedy set.
You need to record this for the next conference. Huh?
It is recorded. So yeah, well, the recording will be up on YouTube later this week. Yeah, I mean, hopefully you guys can tell I'm pretty excited about this. It's a lot of fun stuff. We're learning, we're learning Rust. Rust is a great programming language, especially if you're coming from C. Yeah, and we're having a lot of fun with it. I recognize that obviously this is a sort of new use case for ZFS, so it doesn't. Obviously, not everybody is going to use this. It's a new capability that people will use ZFS in new ways, as opposed to an enhancement that's going to make ZFS better for everybody who's using it today. But hopefully, this is going to, make ZFS have some relevant capabilities in the new kind of the way that storage and computing is moving, namely towards cloud and towards more abstract data storage and services. So making ZFS easier to use and deploy in those kind of situations where you're on top of whatever, some weird SMR drives, on top of an object store, you want to be able to move stuff around from VM to VM, as opposed to like, if you're the one implementing the stuff underneath that and you're consuming raw drives, then obviously like the ZFS's existing capabilities are what you need. Cool, thanks a lot. We'll see you all in 4 weeks at the later time. So that'll be July 20th. And I may be on vacation then, so I'll have someone else run the meeting. And but hopefully you've got your dose of Matt Aaron's ZFS monologues this week, this month, and you'll be good for at least 2 months. All right, see you all.
Right.
Thanks, bye.